Oh, bye.
Wait, sir, I have to tell you something.
What's that? Talk to me.
Yesterday, I had my graduation ceremony.
Oh, big up you. How was it? Was good?
Yeah, it was good. It was real long, though, like 3 hours, because it was like math space and then the ceremony,
Okay.
and we finished like around 8 o'clock, and we start around 5.
Oh, okay. Okay. I'm happy to hear that. Happy to hear that. So you graduated. It's a big achievement that I come this far. Right? I really hope you get through with your passes. I know like things tough, your situation kind of tough, but I rooting for you. But you gotta put in the effort too, and you get through. Yeah. I rooting for everybody here. I want to see how they succeed. But congratulations, everybody, on reaching this far. Yeah.
So
So,
I feel after all these exams, I could be dead.
oh, no, Nicola, you're a survivor. You'll be fine. You'll be fine. So let's start electrostatics and circuits, the most exciting topic in physics. So, Nikolai, I'd like you to give this a read for me.
Okay. Static electricity and attraction. Electrostatics is the study of charges at rest. When two insulators are rubbed together, they can produce electrostatic attraction. Matter is made of atoms which have negatively charged particles called electrons orbited around a small nucleus.
Chem people, until you remember that. Chem people, all you know what I'm talking about, right?
Yes, sir.
Yeah, I didn't do chem in a long time. I didn't come in a long time, Ollie. All I know is that this is a nucleus, right? This is a nucleus and it contains equal part protons and neutrons. And then on the shell, there's like a specific order. If I remember correctly, you have two over here. Then you have one, two, like this kind of thing. That's how it is going, Nikolai, or not? Like you have two here in
Yeah.
the first orbiting shell, and then the other orbiting shell, you have 8 electrons.
Yes, sir.
Okay, okay. Yeah, so people are doing chem, you guys should know that. So this is the general structure of an atom. Um, you have protons and neutrons in the nucleus. This is the nucleus. And you see this shell over here, Adil? That's called the that's called an orbiting shell. By the way, guys, people are doing chem. What do you call the outermost shell? Do you remember? Do you guys remember? People are doing chem. Okay, I don't hear anybody, but it's the valence shell. Shina, you know about that? The outermost shell in an atom is the valence shell.
Yes, sir.
Shina, why you stay quiet for, girl? Hey! Oh, yeah.
So because in my head I was like,
Mm.
in my head I was questioning myself. So
Oh, and well, okay, since this atom here only has one shell. By the way, I thinking about starting chem, but I had to brush up on my chem first. But if you guys had to name this element, what kind of element you'd call that? An element with two electrons.
Helium.
Helium. Shina, what about you?
is this helium? Yeah.
Yeah, it is helium. It is helium. And if I remember on the periodic table, helium is second, right? Because hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, freon, sodium, magnesium, aluminum, silicon, phosphorus. You know, helium is the second on the second there. And you can see that it has two valence electrons. So this is helium. But the point I'm trying to make is Adil, Karina, right, Vani. All matter comprises of atoms. Adil, Karina, and Vani, did you guys know that? All matter comprises of atoms.
Yes,
Yes,
sir.
sir. Yeah.
And around the atom, around the nucleus, you have electrons. Now, these electrons, when you rub two materials together, an electron from this material could potentially like I don't want to say rub off, but essentially it could like it could it could come out of the shell and it would make this positively charged. Now, for those of you guys that don't know, an electron has what charge? Does anybody know? An electron has what charge? An
Negative.
electron has a negative charge. So if you rub an insulator, and if you rub an insulator, right, and some of the electrons rub off on the other material, and this loses electrons, it becomes positive or negative. If it loses electrons,
Positive.
do you guys understand that? Adil, if you lose negativity, you become what?
Positive.
Exactly. So that's what the statement is saying. Electrostatics is the study of charges at rest. When two insulators are rubbed together, they produce electrostatic attraction. Matter is made of atoms which have negatively charged particles called electrons orbiting around a small nucleus. Yeah, Nikolai, I see you raise your hand.
Does the insulator have to be the opposite of negatively charged, or it could just be neutral?
It could be neutral. Could be neutral.
Oh, okay.
Yeah. Do you all know about the electrostatic series?
No.
Then and that is with the circuit with all the things going in one direction.
No. The electrostatic series gives you a list of materials and their tendency to gain electrons or lose an electron. So let me show
Okay.
you guys what I mean. Because Nikolai, when I rub two insulators together, you know that on the outer shell you have electrons. And I'm saying that when you rub two materials together, there's a chance of an electron either leaving or it's actually accepting an electron. So Nikolai, here what I'm saying, right? If you're rubbing a material on another material, right? Let's just say you're rubbing a balloon on like a piece of wool material, right? Like cotton or something. You're rubbing a balloon against cotton.
Yes, sir.
The rubbing motion might cause some of the electrons to leave the balloon and be attracted and actually go on the cloth. And that would make the balloon positively charged and the material they're rubbing it on, the cloth, negatively charged. And anytime there's a difference of charges, there's attraction. That's essentially electrostatics explained quickly. Let me just put the electrostatic series on the screen. Sheena, you really good in chemistry. Did you know about the electrostatic series?
No, sir.
I don't think teachers teach it in school, you know. I don't think so.
I never heard about this, sir. So it's new to me.
This is the electrostatic series. So using the electrostatic series, determine the charge that each material will gain when the two are rubbed together. Amber and cat fur. So this is an example, right? So Nikolai, first we'd have to identify where amber is. I don't know what amber is, but we're just gonna work with her. So amber is over here. Now when you look at this, right, amber has a what? Does it have a tendency to gain electrons or lose electrons?
Gain.
Yeah, because over here, it's stronger tendency to gain electrons. And everything over here has a weaker tendency to gain electrons, so it might lose electrons.
Actually, sir, this is a very important table because in the physics exam, when they ask you about an experiment
Yes?
between wood and the other materials, and they would ask you if there would be opposite charges or anything like that.
Yeah. I don't know.
How come my school never? Okay.
I don't know. But it's good to know. So amber is over here, right? This is where amber is. Where is cat fur?
Above it.
Above it. So which one has a higher tendency to gain electrons?
The amber
Wait, eh? So Karina,
gain.
let me take it a bit slower. So as you can see, the arrow is in this direction. Over here, you're seeing stronger tendency to gain electrons. So the ones that are closer to the bottom of the arrow have have a what, Karina?
A stronger,
Yeah,
stronger tendency
a stronger tendency to what?
to gain electron.
Correct. A stronger tendency to gain electrons. So which one would gain electrons? Which one would have a higher chance of gaining electrons? Tell me, Karina.
The amber,
Exactly. So if the amber has a higher chance of gaining electrons, then would it be positive or negatively charged when it gains electrons?
negatively charged.
Right. Adil, Vani, Shin, I hope that makes sense, right? If it has a higher tendency of gaining electrons, and electrons are negatively charged, if it gains negative charges, it's negatively charged because it's more negative now. You all understand what I'm saying?
Yes, sir.
And I want you guys to tell me which one would have a higher chance of losing electrons, Cat or amber?
Catford.
Right. So what's gonna happen here? What's gonna happen here? So when you rub the amber on the cat fur, tell me, Nikolai, what do you think would happen?
From the catford, there will be electrons being lost because of the amber taking in the electrons because of a stronger tendency.
Yeah, that's a decent explanation. And so the cat fur would now end up positively charged, and the amber would end up negatively charged. And you see there that would create a sense of attraction because you have oppositely charged particles. Anytime you have opposite charges, there's a force of attraction. So that's a quick explanation. When we do this topic more, you'll get a greater appreciation for it. Yeah. So in the normal state, the atom has an equal number of electrons and protons. Could anybody remind me? Protons. Protons are how are protons charged? Positively charged or negatively charged? Protons.
Positive.
Right. Protons are positively charged, and electrons are what?
Negative.
Yeah, electrons are negatively charged. And if there's an equal number of electrons and protons, that would make my object, what? Would it make it positively charged, negatively charged, or neutral?
Neutral.
Karina, Vani, Adil, Shina, does that make sense? If there's an equal number of positive and negative charges, what would happen?
It'll become equal.
Neutral.
Neutral, yeah. Imagine if I had plus 5, so 5, what's it? Imagine I had 5 protons, so plus 5, and imagine I had 5 electrons, that's negative 5. What's negative 5 plus 5?
0.
0, sir.
0.
Exactly. Cool. So I really hope you understand that concept of neutral charge. Therefore, we say that it is electrically balanced or uncharged. At times, when rubbing a surface, electrons are removed from the orbit and the object becomes positively charged. Didn't we already discuss that?
Yes, sir.
Right, we're familiar with that. The electrons are going to essentially, quote unquote, leave the orbit to go to another material, depending on its position in the electrostatic series. Cool. The object that the electrons rubbed off on then become negatively charged. All if you like, all you understand it?
Yes, sir.
Let's do a quick recap. Under normal circumstances, objects are what? Positively charged, negatively charged, or uncharged?
Uncharged.
Karina, Vani, Adil, Sheena, I want to hear you guys.
Uncharged.
Right? Nikolai, that's you? Nico. Mirage. Nikolai Mirage.
Yeah.
Alright, Nikolai, do you know that all matter is made up of atoms and atoms have electrons on the orbits? Yeah or not?
Yeah.
So what I was saying is if you take a material and you rub it against something, some of the electrons could essentially leave the orbit. And if you lose electrons negative, right? If you lose negativity, it becomes positive. And well, the material that gains the electrons will become negatively charged. That's the whole concept. So, Fanny, if I have an object here and I just have an object here, I didn't do anything with it, what would the charge for it be? Tell me, Vani. I just have an object there. I didn't do anything with it. What would the charge be? Would it be charged?
Positive.
Nah, Vani, if you just have an object there, it's uncharged. It's uncharged.
Ah, sorry.
That's okay. Now, if I take this object and I rub it on another material, what could potentially happen? What could potentially happen?
In like electrons or
Say that again, Vani?
it could get charged.
Yeah, it could get charged, and why? Don't be scared, Vani. We're learning. Why? Why could it become charged?
It could gain electrons.
Right, because of the electrons. Vani, anytime you rub two materials together, what could happen to the electrons?
It could like transfer to the other object.
Exactly. So electrons from the orbits would be removed and it'd be transferred to the other object. The object that gains the electrons, would you say it's positively charged or negatively charged?
Negatively.
Good. The material that loses the electrons, positively charged or negatively charged? Losing electrons. Positive or negatively charged?
Positive.
Exactly, because Vani, if you're losing negativity, where you be coming?
Positive.
Exactly. So I hope we understand that. That's the essential concept of electrostatics, of static electricity. So you guys will copy this for homework. I feel like if I give a little copy this now, you're gonna take a long time. Yeah. How long would you guys take if you had to copy this down?
Yeah, I would take a while to take this down.
Okay, well, I trust that you guys will copy this down for homework then. I trust. So let's look at a quick example. Alright, so we have glass rod and silk rod. Alright, I'm gonna give you all an exercise to do quickly. And I trust that you all could figure it out because you guys are really smart. So let's just say we had a glass rod on a silk cloth. So Vani is gonna help me with this. Vani, big up yourself one time. Yeah, Vani gonna be helping me with this. So Vani, let's just say you rub a glass rod on silk cloth. How are we going to figure out which one is gonna gain electrons and which one is gonna lose electrons? That's the question. Vani?
Yes, sir.
Yeah, so Vani, don't be scared. It's fine, you're learning. First of all, Vani, which one has a higher tendency to gain electrons? The glass or the silk?
The glass.
Wait, yeah. To identify that, we're gonna look at the charge tendency. So like, if you look at the arrow,
Oh,
it goes from weakest to strongest tendency to gain electrons. So Vani, if you're looking at that, which one has a higher tendency to gain electrons? Glass or silk?
silk.
Right. Because silk is over here. Tell me if you understand that.
Yes, sir.
Silk is over there. Where's glass?
Above here and here.
Exactly. So tell me, which one would quicker accept the electrons, would gain electrons?
Silk.
So therefore, silk, if silk is gaining electrons, silk would become what?
Negative.
Yes, silk will become negative, and the glass rod will become what?
Positive.
Yep. So Nikolai, this is very important because once you could identify where two materials are in the electrostatic series, you could figure out if you're going to gain electrons, if you're going to lose electrons. So I don't know why they didn't teach students this in school.
So they can at least give you a piece of paper, well, a piece of document on this instead of just not giving me anything on it.
Yeah, at least you learn about it now. Sheena, you ever learn about this?
No, sir.
Nah, wait. So, as you guys will see, watch. Now you actually understand why the glass rod becomes positive and the silk cloth becomes negative. And the reason for that is because the glass rod is going to what? Tell me, Adil, the glass rod is going to what?
Because like Arab against the electrons.
So the glass rod is being rubbed against the silk cloth. So the electrons in the glass rod are going to do what?
Rub against the electrons in the silk cloth.
I do why you say rub against the electrons. It's going to rub against the silk cloth, and because of the friction and because of the movement, you're going to have some of the electrons over here being transferred. Some of the electrons are going to be removed, and it's going to go onto the silk cloth. So Adil, let's try to write a statement. So Adil, some electrons from the glass rod. See if we can finish my sentence, Adil.
Some electrons from the glass rod when rubbed on the silk cloth, the electrons from the glass rod are transferred into the silk cloth.
Okay, that's not bad, but we could refine that a bit. Let me just change up the statement quickly. So when the glass rod is rubbed against the silk cloth, some electrons are removed and transferred. Or the proper thing we should say, and is gained by the silk cloth. If you want to be extra fancy, this is where you could say, Nikolai. You could say, and the reason for this, right, Nikolai, is because the glass rod is lower in the electrostatic. Was it lower? Which one was lower? A silk. Yeah. So Nikolai, if you want, you can say the reason for this is because silk is lower in the electrostatic series than glass. Understand?
Yes, sir.
Silk is lower. So when I was in Form 5, I used to like go and find extra information. So like I'd write an exam answer like this in the exam. I would even if they didn't tell me, I'd do some research and I'd see why it works. And I'd make a statement like this. So silk is lower in electrostatic series than glass. I would always encourage curiosity. I know they say curiosity killed the cat, but you know how to kill all you. Okay.
2 points, sir. 2 points.
Okay.
Still find that the teacher should have gave us a table like that to make life a bit easier than trying to figure out what they gave you in the question, which one would lose electrons and which one would gain electrons.
I know it. It kind of frustrating. But now you have this table to refer to so you can compare two materials seamlessly. So the one that loses the electrons become positive charged, and the one that gains the electrons become negatively charged. So it should be noted that only wait, let me ask somebody else to read. So Nikolai Mirage, read the summer. Nikolai. Okay, like Nikolai kinda shy today, boy.
Yeah, don't mind or
Yeah, you can read it.
okay. It should be noted that only the electrons will move because they are much lighter than protons. Protons are also bonded to the nucleus, which make them unlikely to move due to friction. If a plastic rod was used, it would gain electrons instead.
Right. So let's try to understand this, right? It should be noted that only the electrons will move because they are much lighter than protons. Do you guys remember the weight? Well, I shouldn't say weight, right? I should say mass. Do you guys remember the mass of protons and electrons?
Yeah.
Because you had to know this in physics and chemistry, you know. So if you guys remember, the relative mass of protons, I'll just do this. The relative mass for protons. Anybody can tell me what's the relative mass of protons? Come on,
And
guys.
would that be the neutrons minus the electrons, or would that just be the electrons? Because I know that. No, no, that wrong answer. Sorry.
Nah, the relative mass of a proton is 1. And if you're looking at the specific mass in kg, the specific mass in kg is really 1.67. I don't know why 67, you know, but it's 1.67 by 10 to the power minus 27 kg. So that is protons. Could anybody tell me the relative mass of a neutron? Anybody? Relative mass of a neutron.
What?
Yeah, it's 1. And in kg, that's 1.67 by 10 to the power minus 27, right? Right, Karina? And Karina, do you know what the relative mass of an electron is?
Not quite.
Not quite. That's not a problem. It is 0.0005, and in kg you would see 9.11 by 10 to the power minus 31 kg. I need to make some notes on this. Add page after. Okay. Yes, so these are the relative mass of protons, neutrons, and electrons. This is the general structure of an atom. You know, it has a nucleus, electrons orbiting on the outside. This is the electrostatic series. So I'll just put in all the extra notes on a different page. Okay. So let me ask a question, right? Looking at the relative masses, which one is the lightest, Karina? Which one is the lightest? Which one has the smallest mass?
The electrons.
Exactly. So, Karina, if something has a lower mass, doesn't that mean like it's easier to move according to Newton's law?
Yeah.
Yeah. Which law of motion is that? Could anybody tell me? I really asking all some random questions, but because it's important to tie in everything. Could anybody in class tell me which law of motion, which Newton's law talks about mass?
The first one?
Yes, yes, the first one, which is the law of inertia. It says an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the exact same direction unless acted upon by an external unbalanced force. And inertia is just a tendency of matter to resist change in its velocity. The more mass something possesses, the harder it is to move. Karina, doesn't that make sense? Imagine a truck compared to a feather. Which one would be easier to move?
The feather.
Exactly. So in the grand scheme of things, Karina, the protons and the neutron, them come like big truck. The electron come like a feather. So which one would be easier to move?
The electrons.
Perfect. So I hope you understand this statement over here, which says it should be noted that only the electrons will move because they are much lighter than protons. Protons are also bound to the nucleus, which make them unlikely to move due to friction. So I hope you understand the first part over here, where electrons are much lighter than protons. And you should also understand that protons are bounded in the nucleus. Protons are literally fixed into the nucleus. They can't really move. You would need to do nuclear fission or fusion if you want to like split an atom. You can't really. It's a little. You see, like, okay, this, only 4 and 5 people will get this. Nikolai, when you do nuclear fission or fusion, what happens?
Fission and fusion.
Yeah, you do that yet?
In the radioactive decay.
Yeah.
Fusion is when it combines, fission is when it separates into two identical daughter cells.
Yes. Yeah. But generally speaking, guys, the proton is locked into the nucleus. It can't be moved. Unless you like you put real energy into it. So I really hope you guys understand the statement over here. If a plastic rod was used, it would gain electrons instead. But why? Again, these are not my notes. Big up to Kevin Jarrett Bosine. This is his notes. Right? But he did not state why. So, but now you know why, right? Because of the what? Because of the what? Can anybody tell me why? If a plastic rod was used, it would gain electrons instead. Because what? Why?
Because the plastic is more than the glass is lower down.
Good. You have to talk about the electrostatic series. So, Shana, I'm going to call upon you. Shana, do you see the statement over here, Shana? For us to understand why the statement is true, we need to look at the electrostatic series. So, Shana, if we look lower down on the electrostatic series, those materials have a higher chance of gaining electrons or lower chance of gaining electrons.
Higher.
Say that again?
Higher.
Higher. So, which one do you think? So, okay, we're comparing silk to plastic. And they're saying over here that if a plastic rod was used, it would gain electrons. So that would mean that plastic is higher above than silk or lower than silk in the electrostatic series.
Lower.
Exactly. Plastic would be lower on the electrostatic series. And let's verify that quickly. Silk is over here. And you see like vinyl, polyester, essentially plastic, rubber. Yeah. All that is lower down. So let me know if everybody is understand with the definition of electrostatics. It's just a study of charges at rest. Do you guys understand electrostatic attraction? If you don't, just remember that attraction happens when you have oppositely charged particles. So Adil, Nikolai Mirage, Anna Nikolai, Karina, Amira, electrostatic attraction is, first of all, attraction is just attraction happens between two oppositely charged particles. And if you rub one material on another material, one material could potentially lose electrons and the other material could potentially gain electrons. The one that loses electrons becomes positive positively charged, and the one that gains the electrons becomes negatively charged. That imbalance in charges creates electrostatic attraction. So I hope everybody understands that. Cool. Now we're going to look at charge, current, and time. So, Amira, I want you to read this for me.
Charge is measured in coulombs. 1 coulomb is equal to 6.25 multiplied by 10 to the power of 18 electrons. Devices that store charge are called capacitors and gain current as time passes. It should be noted that time plays a major factor in terms of charge.
Do you guys know what a capacitor is? Does anybody know what's a capacitor? I feel like, Karina, you know about that?
The limit?
Nah. A capacitor is just an energy storing device. That's really all. So you know how a battery just store energy?
Yeah.
Capacitor to store energy. Granted, a lot less energy, but it is store energy nonetheless. Have anybody here in take audio or anything?
Nah, not really. Not as yet.
Well, Nikolai Mirage, I feel like you in take audio. Is my suspicion correct?
Yeah.
Okay, you know that capacitor?
What?
You know that capacitor?
I think so.
Well, let me show you. So, car audio people, typically, before hooking up, like you wouldn't directly hook up the battery to the amp. You typically put a capacitor in the middle. And why is that, Nikolai? The reason for that is because bass, like okay, you see like bass, it's a very the frequency of bass, like bass notes, is very low, so it draws a lot of current. Nikolai, it draws a lot of current, a substantial amount of current. And so putting the capacitor there acts like a reservoir. So like if the amp pulls too much current, the capacitor will be there to deliver the current, and it'll be essentially like a reservoir. It will like store some charge for the amplifier to use. It wouldn't just pull it from the battery.
Oh, okay.
Yeah. And so you know how it would have water tanks. Okay, so like water would come from Wassa. And you'd also have some tanks just in case water goes. Do you all know that?
Yes, sir.
Okay. Doesn't the tank store some water in the event that the water stops, the water cuts?
Yes, sir.
Well, a capacitor is the same thing, A capacitor is the same thing. It just stores electric charge. So if the charge from the battery stops, well, the capacitor would be able to supply some charge, while the battery while the if we're talking about car audio, the bass notes would pull a lot of current, and when the bass notes stop, it would start to pull less current, so the capacitor would charge back, and it would start pulling current from the battery again. It's like a tip. It's like a short explanation. Nikolai, you ever see anything like this?
I believe so, but I don't remember.
Oh, I'm talking about the other Nikolai, because he said he in the car audio.
Oh,
Yeah, I see something like that, but smaller.
Yeah, well, it's a capacitor. It's a capacitor, right? And it stores charge, so it acts like a backup, or like just something for the amp to pull from. Because capacitors, they discharge really, really fast, but they have the ability to store a lot of current and disperse it and discharge it really, really fast. So that's the property about capacitors. So guys, capacitors, they store charge and could discharge, or they could charge and they could discharge real fast. So Nikolai, you know how a battery just take like a couple hours to charge?
Yeah.
yes, sir.
A capacitor could charge in a couple seconds, seconds or minutes. Yeah, but it will also discharge in like a real fast time. You know how a battery would last for like an hour, like a couple hours?
Yeah.
Yeah, a capacitor would last typically a couple seconds for the most. Couple seconds to a minute. Supercapacitors would last minutes, but generally speaking, capacitors they charge and discharge really fast. But Nikolai, both Nikolais, and anybody in class are listening. The special thing about capacitors is that when they're discharging, they could discharge a very large amount of current. And Nikolai Mirage, that's why we just use it in car audio. Because when the bass playing, it put in real current. So you want a capacitor there so that when the bass note hits, it can pull the current from the capacitor instead of the battery. Because the capacitor would be able to like supply a lot of current real fast. You
Yeah,
understand?
for them base because we pulling real current and then it could blow.
Exactly. So I hope you understand the importance of a capacitor now. That's what capacitor does do. It store charge temporarily and it's act like a reservoir. So Amira, I'm not sure if you're into electronics and thing, but here's a simple example, right? Right, Amira? You know how a battery does store charge and it lasts real long?
Yes, sir.
A capacitor does do the same thing, but it don't really last long. It is charge and discharge real fast. Yeah. But it is an energy storing device.
Because
So yeah, the point is it is store energy, that's all. And anything that stores energy would typically store a charge. Yeah. So Amira, charge is measured in coulombs. That's what we just measure charge in. 1 coulomb is equal to 6.25 by 10 to the power 18 electrons. If I do copy anything down today, I want to copy this down. Copy that down from now. This is very important information. Charge is measured in coulombs, and 1 coulomb is equivalent to 6.25 by 10 to the power 18 electrons.
One question, so would they give that specific number in the exam?
Typically they would, but you should remember it just in case.
Okay.
Never be too sure. Okay. And again, if it's one thing I want to learn from my classes is like understanding thing. Don't just read it and learn it off. I try to understand what it means. Understand it. Right. So I think I've taken all I have it copied down there. So tell me,
Yeah.
how much electrons are in 1 coulomb? Coulomb is represented by capital C, by the way. How much electrons are in 1 coulomb? Somebody tell me how much
6.25 times 10 to the power 18.
Let me ask somebody else. Amira, my good friend. How much electrons are there in 1 coulomb? Okay, I catch Amira. It would seem. Adil. Okay, I see she on mute. Yeah, Amira, how much electrons are there in 1 coulomb?
10 to the power 18.
Nah,
Oh,
6.25 by 10 to the power 18 electrons. Which is a lot, Amira. 10 to the power 18, you know how much zeros that is? That's 18 zeros, you know. Amira, if you had okay, imagine seeing 6.25 followed by multiplied by 1 followed by 18 zeros. That's a lot of money, right?
yeah.
Like you could probably live like that go on serve your hey. That amount of money is unprecedented. That's insane. That's insane. You know how much zeros a billion is, right? How much zeros is having a billion? You know? I think it's 9. Yeah,
There's
it's 9.
9. That's 6 in a million.
Yeah, so Amira, just think about that for a minute. This is a billion is 9 zeros. This is that's to the power 18. What do you call that, boy?
What is a trillion? So a trillion higher than a billion, eh?
Yeah, but this would be a quintillion. This is a quintillion. Yeah, this is quintillion. Quintillion. 18 zeros. So that's a lot of electrons, right, Amira? You agree?
Yes, sir.
Okay, one more time. How much electrons you have in one coulomb?
6.25 multiplied by 18 10 to the power 18.
Cool. Good. So charge is measured in coulombs. 1 coulomb is equivalent to that. Devices that store charge is a capacitor. And they gain current as time passes. So, question, guys, when you put your battery to charge, when you put your phone battery to charge, and as it charges, you see like the percentage go up.
Yes, sir.
Right. So let me explain something. As batteries discharge, the amount of current they could output decreases. So when you charge in your battery, the current builds back up and it can power your phone. All electronic components pull some current. And as your battery dies, it supplies less and less current. So Nikolai, that is why you gotta charge your battery so that the electronic components in your phone would get the current it needs.
Yes, sir.
And do you guys know what the definition for current is?
Hmm.
There's anything that stores energy, I think.
Nah, that's a capacitor.
So I give up.
No, don't give up, right? We didn't even
Not
look at that yet.
really, sir.
I am just trying to explain things ahead of time. I'll put a definition here so you guys don't get confused. So does everybody understand what charge is?
Yes, sir.
Okay. And basically charge is the amount of electrons something have, right? That's it. I'll make a note about that. Charge okay. Amira, tell me fast. How much electrons you have in 1 coulomb?
6.25 multiplied by 10 to the power 18.
Good. What do you call devices that store energy? Or devices that store charge?
Capacitors.
Good. Could you give me an example of something else that stores charge? It is used it in your phone. It is used it in your...
Batteries.
Yeah. Cool. Hope we are okay with that. Next thing. What does current mean? First of all, current is written by a capital I, and it tells us the amount of charge passing through a point in a complete circuit. Right? So I'll make a better note about it here, but this is just a basic concept. It's just simply the rate at which electric charge right? And again, we know that charge is the amount of what? Charge is the amount of what? Charge is the amount of... Somebody remind me. Charge is the amount of...
Electrons.
Good. Charge is the amount of electrons. The more electrons something could store it, the greater the capacity of the battery or the capacitor. Um, right. So this brings me to one of the most important equations you have to know. But before I do that, you need to understand that, okay, see how I'm using a capital I for current? And let's see in that, right? A capital I for current. Current is a capital I. Let me know if you're seeing that.
Yes, sir.
Yeah. Current is a capital I. What do we use for charge?
Q.
Right, for charge, we use Q. And we measure charge in what?
Coulombs.
Yeah, measured in coulombs. And how much electrons it have in a coulomb?
6.25 times 10 to the power 18.
Yeah. And there's always spell this man name wrong, you know. Always. So I have to check there. And we should also understand what we measure current in. Does anybody know what we measure current in? Nikolai Mirage, he's a common, you should know.
The amperes.
Yeah. Nikolai Mirage, and you know that's a current, like you see like that speak up in real amps boy, real current. You know what I mean?
Yeah,
Yeah.
of course.
Current is measured in amperes. Amperes is given by a capital A, and coulombs is given by a capital C. So there must be an equation that relates charge and current together. Must be. So what did I say about our energy storing device? I said that as time increases, what would increase? For a capacitor, as time or battery, as time increases, what increases?
The charge or the current.
Yes. Amira, Mirage. I'll say Amira, Nikolai Mirage, Karina, Adil. In any energy storing device, as time passes by, the amount of charge increases. So the current increases. I hope all you understand that. Okay, so Adil, let me just summarize what I'm saying, right? So Adil, as time increases, right? What else increases?
As time increases,
Yeah, as time increases, we're increasing. Like, okay, here think of a simple example, right? You put your phone to charge. As time increases, we're investing about the percentage.
it went up.
Right, so as time increases, the charge what? What does happen to the charge?
Increases,
Ollie, what kind of relationship is that? Proportional, inversely proportional.
proportional.
Yeah, at least you have a time in the maths into this, Shina. Nikolai. Until you could see that this is a directly proportional relationship because as time increases, the charge increases.
Yes, sir.
Yes, sir.
Yeah, and the constant of proportionality here would be Q. I'm saying it wouldn't be Q, right? It would be I. It would be I. Yeah, because the formula that we're going to talk about is Q is equal to IT. And does anybody know about that formula?
Yes, sir.
Okay, if you didn't know, damn us a man to say on what you know. If you didn't know, now you. If you
Now
didn't know, now you know. Right. So this over here is a proportional relationship. I should say directly proportional. That's where it is. In the form, was it the form 4 or form 5 class? I had form 5 class I had explained this. No, in form 4 class. In the form 4 class, I'd speak about the difference between directly proportional and proportional. Yeah. Wait, so directly proportional. And so, Amira, could you just remind me what Q stands for? What does Q stand for?
Um,
Check back the notes. What does Q stand for? Q. What does Q stand for?
charge.
Right. Q stands for charge. What do we measure charge in?
Coulombs.
Exactly. Measured in in this smart blasted name, boy. Hey, coulombs. Yeah, measured in coulombs. Cool. Could anybody tell me what I represents?
Current,
And current is measured in what?
amperes.
And time is measured in what? Typically in physics. What do we measure time in?
Seconds.
Yes, we measure time in seconds. So hopefully seeing the directly proportional relationship I was talking about. And in this case, I would be acting as K, the constant of proportionality. Yeah. Let's see what I'm talking about or no? Shana, uniform for class. Shana, you think you can make the connection between this and what we did last class in maths? Or not? I'm not sure if you was there. Were you there in last class?
No, sir. But I did start to watch the recording.
Okay. Shana, all I'm saying is when one quantity increases, the other one increases. But by how much? So that's the role I plays. So Q is equal to IT. Make sure you have this copy down. That's very, very important. Q is equal to IT. 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 Now let me show you guys something cool. So again, somebody tell me, what's the formula other than Nikolai? Other than Nikolai McLeod? Somebody else. What's the formula for charge? Remind me, what's the formula?
Q is equal to IT.
Q is equal to IT. If we were to make I the subject of the formula, what would I do, Shina?
To make I subject of the formula,
Yeah,
divide both sides by T.
I'll divide both sides by T because I'd want T to cancel off to leave me with I. So I would be equal to Q all over T. So I hope we understand that. And Sheena, this is the part where blow your mind, right? Remind me, Q is what again? Q is a measure of what? That's what? That's what?
Charge?
That's charge. And T, where we have in the bottom?
Time.
Anytime you're dividing something by time, it's typically a rate, correct?
Yes, sir.
And so remember this, charge over time. So just by looking at this, Sheena, how would you say that, describe that in English? You would say that current is the what? By looking at this relationship, charge over time, what would you say current is? So again, anytime you divide them by time, you're talking about rate. So Sheena, see if you can figure it out. Charge over time, what does that mean?
The rate of electric charge.
Exactly the rate of which something charges. And if you remember, I said the current is the rate at which electric charge flows past a point in a complete circuit. So I hope you all could see the connection here, where I say current is equal to charge over time. Nikolai, do you understand what I'm saying or not? Because it's charge over time.
Which one?
Say that again. Wait, are you hearing more now?
No, so we hear about you is lagging a lot just now. We're now hearing you. No.
Okay.
Other than that, I do understand, sir.
You do understand? Well, if you're still confused, let's bring back the definition of current. This is what I told you guys current was. So a mirror, right? Anytime you're measuring something with respect to time, that's typically a rate we're looking at. Do you understand now or not? I'm telling you that anytime we're talking about time, we're talking about a rate. You understand now or you're confused by
Yes,
that?
sir, I understand. Yes, I understand.
Okay, good. So you understand why I say in the definition for current, is the rate at which electric charge, because it's charged over time, the rate at which electric charge flows past a point in a complete circuit. That's what
Yes,
current.
let's say that the time at which the electric charge flows past a point in
That's
the
it.
circuit.
That's fine. Earlier in physics, if all you ever forget a definition, just use our formula probably and just write the formula. Make something, make way trying to find the subject of the formula and see what units it is, and that'll guide you accordingly. Physics is really cool. I love physics. Physics is goated. So using this formula, I could actually figure out quite a lot. So let's just jump to some questions one time, shall we? So Nikolai, as time increases, what increases again?
Current or charge.
The charge. Because as time increases, you'll have, okay, remember, okay, and next thing, current would always go from a lower potential. What's saying? It would always go from a higher potential to a lower potential. I'm not sure if you guys knew that. 4 and 5 people always should know that.
Yes, sir.
Yeah, current always goes from higher potential to lower potential. I'm probably saying, what the hell? So what do you mean by that? Let me ask Olia a question, right? Olia, talk to me. When your phone dead, what charge do you think your battery has? Amira, talk to me. When your battery dead, what charge do you think your battery has?
0.
0. And your charger, right? Your charger, isn't your charger gonna have a high? Okay. If you, Amira, just think about it logically, right? Your phone dead. Would it have a low potential or a high potential? Potential just means like voltage or something. You think of potential as voltage. Your phone dead. Do you think it have a high potential or low
Take
potential?
it yourself, please. You just break up.
Right. So Amira, when your phone is dead, that means the battery has 0 charge, right? You guys hearing me or not?
A low potential.
Yeah.
Yeah.
So you're breaking up.
Give me a second. Let me know if you're hearing me. Are you guys hearing me? Sound check 1 1. Sound check 1 1. Let me know if you're hearing me.
Yes, sir.
Yes, sir.
Alright, so Amira, when your phone is dead, the charge of your battery is effectively 0. So you would say that has a low potential. But you need literally remember Amira, you're literally taking the charger block, you're sticking it into the wall. So would you say that has a high potential or a low potential?
So what, the charger block?
Yeah, the charger block. You're literally sticking it into the wall. Has a high potential or low potential?
A low potential.
No, a high potential. Okay. Right now, just think of potential as voltage or the amount of charge something possesses. So, Amira, do you think your charger block has a lot of charge or a low amount of charge?
A lot of charge.
Exactly. So, if your charger block has a lot of charge, ain't you want that lot of charge to go into your phone with 0 charge?
Yes, sir.
So the current is going to leave the charge. It's going to, I wouldn't say leave, but the current is going to go from the charger block to your what?
Phone battery.
Exactly. So the current is going from an area of what potential to what potential?
High potential, so low potential.
Good, good. Yeah, yeah. It's
So
very
it's
important.
like osmosis.
It's a lot of concepts in science follow the same thing, high to low. Um, I don't know if I remember diffusion. Diffusion is like the same thing as well.
Yes, sir. It's just in the opposite direction
Yeah.
and to evenly distributed.
Yep. And Yeah, like okay, if you think that okay, if two things have the same charge, do you think current will flow?
No.
No, it wouldn't. Amira, it wouldn't. Amira, it wouldn't. If two things have the same charge, no current will flow. But if something has a lower charge, the current would leave the place of higher potential and it goes to the place of lower potential. Yeah. Okay.
Understood, sir.
Good. I really hope all you understand any concept. That's the main thing I'm trying to preach right now, the concept. Let me do the question. So when you understand the concept, the intuition will make sense. So who wanna help me with this question here? I see Nikolai raise his hand. I'm gonna ask Karina. Like Nikolai, I'll get Karina a chance. Karina, read example question 1 for me.
During a certain lightning strike, a current of 5 times 10 to the power 4, a flow for a time period of 0.15 milliseconds. Calculate the quantity of charge of the lightning strike.
Right. So during a certain lightning strike, a current of what? So Karina, let's underline current 1 time. So they're talking about current here. What symbol do we use to represent current? Is it a T, a Q, a I? Current, what's that? What's current?
I
I. So let's write that down 1 time. They're telling us that I is equal to 5 by 10 to the power 4 amps. Yeah?
yeah.
Okay. And they're telling us that the current would flow for a time of what?
0.15 milliseconds.
So they're giving us what there?
The time.
Right? Let's put that on 1 time. Telling us the time is 0.15 milliseconds. Now, just remind me, guys, anytime you see milli means 10 to what power? Well, Karina, you tell me. What does milli mean? Milli means 10 to what power?
What is um yeah, I'm not sure.
That's okay. But you should after today, you should remember it. Let me give you a table quickly. Yeah. Please, after today, don't forget this. Karina, don't forget this after today. You have to tell me now, Karina. Milli, what does milli mean? Tell me standard form.
Standard form is 10 to the power of negative 3.
Right, so that's 0.15 multiplied by 10 to the power negative 3 seconds. That's what it means. Okay,
Okay.
cool. Right, and what do they want us to calculate?
The charge of the lightning strike.
Good. What formula has Q, I, and T in it? Tell me, Karina, what formula are we talking about here?
Q equal to IT.
Right, Q is equal to IT. We want to find for Q. Q is just charge by time. And you know, this make real sense. I'll give you a quick, easy example of this just now. So, Karina, a way to understand that charge tells us the rate of current, right? It tells you like how much current. Okay, current tells you how much charge passes in 1 second. That's what that's what current tells you. So I say it again, Karina. Current tells you how much charge is passing a point in 1 second. And Karina, how much time do we have?
We have 0.15 times 10 to the power of negative 3.
Right. So Karina, what does current tell you? Current tells you the amount of charge per second. Right? Charge per second. And the time is 0.15. So Karina, let me get a real easy example, right? If I tell you, Karina, that in 1 second, you're gonna have a charge of 5 coulombs, right? If I tell you, so Karina, every 1 second, 5 coulombs, and I tell you it was on for 2 seconds, how much charge will I flow? How much charge will I have got?
20 seconds.
20?
I mean 20.
Now
20 wait. 2 seconds, that'll be 10 columns.
10 coulombs. All you understand the intuition behind this thing? Because again, current is just telling us the rate at which charge is moving. That's all. That's what current tells us. So like, this is a quick example. Every 1 second, 5 coulombs of charge flows. And if it's on for 2 seconds, then 10 coulombs would happen. 10 coulombs of charge would have gone to the battery or the capacitor or something. That's literally the basis of the formula. Right? That's the whole point of the formula. Yeah, Nikolai, I see you raise your hand.
So isn't it supposed to be positive 4 and not negative? Because you have 5 times
Yeah.
10 to the
Yeah, I don't know where that negative come from. It's almost like I'm becoming negatively charged. Yeah, so plug that into the calculator and let me know what it gets in.
I got 7.5, sir.
Tiny power or anything?
No, sir.
Yeah, I get into 1.5 too. And your answer would be what? What's the units for charge?
Amperes. No, coulombs.
Coulombs. If I asked you how much electrons this was, how would you find that?
Divide by 6.25 times 10 to the power 18.
Nah, not divide.
Or multiply then. Okay.
That's- Adil, could you remind me how much electrons I have in 1 coulomb?
6.25 multiplied by 10 to the power of 18.
And how much coulombs we have here?
7.5.
If I wanted to find the number of electrons, then the number of electrons would have been the number of electrons would have been 7.5 multiplied by what?
By 10 by 10 to the power 18 by 6.25.
Yeah. So let's plug that into your calculator and let me know what you're getting. And give me an answer to 3 significant figures.
I got 4.69 times 10 to the power 19.
You got, say that again?
I got 4.69. No,
Beck.
you see, yeah. 4.69 times 10 to the power 19.
And that'll be the number of electrons, right?
Yes,
So
sir.
let me explain what happened, right? So Nikolai, in 0.15 milliseconds, the lightning was able to transfer 4.69 by 10 to the power 19 electrons to where it struck. You understand?
Yes, sir.
Yeah. So if that was you, the lightning would have transferred 4.69 by 10 to the power 19 electrons into your body. Which would
And
have
I
been,
would have been cooked.
yeah, you'd have been cooked. So I hope all you understood the concept there. So this is the answer. They asked us for they asked us for the quantity of charge. So this is the answer. But this was an extra question. Extra question. Extra question. So I'm going to give you all a question to do on your own now. So how much time will I think I need for this?
Not much.
Okay, well I'll give all you 4 minutes. Go.
Finish.
Okay, so my answer not a little bit correct.
Yes, sir. I just write the equation and the workings, yes, sir.
Huh?
I only wrote the equation of what I'm using and the workings as to how I got my answer.
What's up, man? Still, I want to see where you. I want to see where you do. Let me tell you if this is correct. Yeah, that's correct.
Yes, sir.
Good job. And Nikolai, let's go into the intuition of it, right? So Nikolai, NC represents Coulomb, which represents the charge. It tells you how much charge. It tells you the charge, right?
Yes, sir.
Cool. And so, which capacity would you think is larger, 4,320 or 9,000 coulombs?
9,000.
Good. So, do you think it's going to take longer to charge it now, or like less time to charge it now?
Last time?
Less time. Here the question again, Nikolai. You increase the battery size.
Oh, yeah, increase.
Yeah,
Oh, yeah. Okay,
yeah,
well, then, no. This is longer then.
because it'll take a longer period of time to deliver the number of electrons it needs. And current is the rate at which electrons pass through, like in a circuit.
Yes, sir.
And isn't coulombs just telling you the number of electrons that have any battery?
Yes, sir.
Right. So
I
that's
thought you were talking about the difference. I didn't pay attention to what question you asked.
oh no. If you look at the question, you will see that the capacity increased, meaning that it would take longer to charge the phone. And that's the logic behind it.
Yes, sir.
Shana, that is correct as well. Okay, time is up. So the persons that didn't tell me answer yet. So Amira, Karina, Adil, Vani, and Nikolai Mirage. Talk to me. All right, number one, Vani, talk to me. Vani, were you able to get through?
Yes, I get you.
What you get for your answer?
7,800 seconds.
Okay, good. Nikolai Mirage, be honest with me. Did you get that or not?
Because I will power water and I'll come back.
Wait, you went for water a long time, wait. Hey. Here what, you do the question, Mama. Right? And it's for your
Now
best
go and do it.
interest.
Now go and do it.
We will do the question together. It's for your best interest. Right?
Alright.
Karina, did you get through?
No, sir. I lost. I lost it.
You lost? Okay.
Yeah.
No worries. Well, experience. Amira, did you get through or no?
No done.
What you get for your answer?
7.8 hours.
7.8 hours. Nah. Remember, the unit's gonna be in seconds. Be 7,800 seconds. Because in physics, that's the SI unit for time. And if you're working with SI units, you're gonna get your SI unit answer. So, coulombs
So
and
in
amperes is.
school, right?
Say that again?
So in school, my teacher, like we do this already, and so okay, all right, don't worry.
No, talk to me, talk to me.
No, so like in school we do this topic already, and like my teacher, like when we was doing the passive questions, she was getting like the answers in hours.
It depends on what the question asks for, but the SI unit for time is in seconds.
So just convert it to seconds or do it over.
Wait, the answer you find, it will automatically be in seconds.
Okay.
You know why or not?
So I don't know, could that be a SI unit?
Yeah, because okay, what's the SI unit for time?
Seconds.
Alright, the SI unit. Well, here what, right? Coulombs is not a fundamental unit, but it's comprised of SI units. Amperes is not SI unit either, but it's comprised of SI units. So if both of them are comprised of SI units, coulombs and amperes, then the answer you get is going to be in seconds. Time is gonna be in seconds. If you did want to convert it to hours, you'd have to divide it by 3600. Yeah. I
No,
feel I feel like I lost you there.
no, so I yes, I confused because in the question I did not specify.
They never specify, so leave it in seconds. Leave it in seconds. If they don't specify, leave your answer in SI units. And that goes for anything in physics, SI units. Yeah.
They say 28,080 seconds.
Nah, that's not correct. Alright, so here what? Amira, Nikolai, and Karina. Let me run it, right? So I'm gonna call Karina specifically. But pay attention, Amira, Nikolai, and Karina. So Karina, give the question I read from you.
The makers of a cell phone have updated its battery capacity from 44320 capacity.
Wait.
No,
What is it?
4320 columns to 9000 columns. If a charger delivers 0.6 amps, how much more time will it take to charge the new battery than the old?
Right, so Karina, they increased the capacity from 4,320 columns to what? Karina, as the first question, they increased the capacity to what? I promise you it's not complicated and it's in the question, you could do it.
You were lagging a lot, I didn't hear you.
Right, so what did they increase the capacity to?
9,000.
Yeah, 9,000. So it went up from 4,320 columns to 9,000 columns. Let me know if you understand that.
Yeah.
Okay. So if I asked you, so our question, right, Karina? Logically, what would take longer to charge? A battery with a higher capacity or a battery with a lower capacity?
A lower capacity.
That would take, wait, what had I asked again? Remind me, what I had asked longer or like shorter time? What had I asked?
Longer time.
And you're saying that a battery with a smaller capacity would take longer to charge.
No, higher capacity.
Higher capacity, because a higher capacity would store what? Would store less charge or more charge?
More charge.
Good. So here what? If we want to figure out how much longer it would take, one way to do it is to figure out how much the charge increased by. So, Karina, the charge increased from 4,320 to 9,000 coulombs. So so the new, so the difference in capacity will be what? So tell me, Karina, how will I find the difference in capacity?
Subtract 44320 from the 9,000.
right? And that would equal to what?
4680.
Coulombs. So, okay, Amira, Nikolai Marash, Fani. Does everybody understand that they increased the capacity by 4,680 coulombs?
Yeah.
Yes, sir.
So we need to figure out. Oh, by the way, Adil, you had got through or no? I don't want to leave you out. Adil, talk to me. Okay, Adil, I see you do something over here. Nah, that's not entirely correct. So, Adil, you there?
Yes, sir.
All right, so Adil, they increased the battery capacity from what to what?
From 4,320 to 9,000.
So if they increase the capacity, would it take the same time to charge or a longer time to charge?
Alondra.
Right, and the longer time to charge would be as a result of increasing the capacity. So if we could find the increase in capacity, which is the difference, we could figure out the extra time it would take. So this over here is going to be the reason why it takes a longer time to charge, right, Karina? Because they increase the capacity. Eh, what, man?
Yes, sir.
So is it possible for me to find this extra time over here? The extra time as a result of adding that capacity?
Yeah.
Yeah. So this is the difference in capacity, right? This is what was added. Do we know the rate at which the charger delivers current?
0.6.
Wait, I say that bad. I really should have say the rate at which the charger delivers charge, which is current. That's what current is. So 0.6 amps. Yeah. So Karina, current. Current is I over here. That's current. And remember, the formula that connects charge, current, and time. What's the formula again?
So that was giving me trouble.
Right. What's the formula that has Q, I, and T in it?
Q equal to IT.
Right. Q is equal to IT. Now the question is asking us how much more time will it take to charge a new battery? And that time would be, well, time is T, right? So we are looking for a formula here that relates charge, time, and current. So that's why it makes sense to use this formula. So Karina, what is the extra capacity? Do we know what the extra capacity is?
Extra capacity would be the 4680.
Good. And do you understand? Because we add that new capacity, it would take a longer period of time to charge.
Yeah.
So we need to figure out the time it would take to charge this extra capacity. And that would answer the question. You understand or not?
Yeah, again there.
Alright, so I'll say it back again. If we know that this is the extra capacity, and they're asking us how much longer it would take to charge a new battery, then we could figure out the time it would take to charge this extra part, because the extra part is where add on. And if you could find the time it take to charge the extra part, that would tell you how much longer it would take to charge a new battery. Yeah or no?
Yeah.
Alright, so what to do next? See if you can tell me what to do next.
Equal to 0.6 by T.
What to do next?
You change the formula.
Right? So I make what the subject of the formula.
T.
So how would I make T the subject of the formula?
You take the 0.6 and divided by the 4680.
Nah. So Karina, I want to find for T, right? If I want to find for T, then wherever T is, T had to be the only thing on that side. So tell me, which side is T on?
T is on the right side.
Right. So I need to cancel off the 0.6. How would I cancel off that 0.6?
You divide both sides by 0.6.
Good. So in maths too, this is important for maths as well. Anytime you're making something the subject of the formula, you need to do the operation that would eliminate what's by the variable. So we need to eliminate what's by the t. So you divide both sides by 0.6. Amira and Nikolai Mirage, when I find time, since we are working with SI units, I'll find the time in what? Seconds or hours? Yeah, it'll be in seconds. What is 4680 divided by 0.6? What are you guys getting for that? I'm waiting, guys. Talk to me. Well, yeah.
7,800.
7,800 seconds. And Karina, that's the answer, you know. Karina, that's the answer. Now,
Yes, sir.
Karina, try to explain the question to me now. Let me see if you fully understand it. There's another way to work the question that's simpler, but I feel like it's more work.
Okay.
Try explaining the question to me.
So they changed the capacity from 4,320 columns to 9,000 columns
Mm-hmm.
with a charge of 0.6 amps. And you have to find the time it takes to charge the new battery.
Right.
So you find the extra capacity by
Mm-hmm.
subtracting the 9,000 by subtracting the 4,320 from the 9,000, and you'll get 4,680 columns. And
Going good so far.
you'll have the same charge of 0.6 amps, but you still don't have the time, which you have the formula of Q equal to IT, which is 4,680 equal to 0.6 by T.
Good.
And then you make T the subject of the formula by dividing both sides by 0.6 to cancel out the 0.6 by T.
Yeah, that's it.
And then you'll have T is equal to 7,800 seconds.
That is it. Excellent. You did a good job explaining that. So Amira and Nikolai Mirage, I'm probably okay with that. Do you guys understand the concept?
Yes, sir.
Now, that's one way you could do the question, right? But there's a more laborious, time-consuming way to do it. So Karina, and any difference in time would just be the time it took to charge the original battery, take away from the time it would take to charge a new battery.
Yeah.
Yeah, so you could find the time it would take to charge the old battery. So I just gonna use the formula for time one time. If you want to find for time, you realize that time is just Q over what Karina? T is just Q over what?
Q over
Alright, so remember Q is equal to IT. If I make T the subject of the formula, I gotta divide by on both sides.
By I.
Yeah, so T is just Q over I. So the time of the old battery, that just be 4320 all over 0.6. What would that be? So Adil, if you understand it, talk to me. Let me know. If you don't understand it, again, talk to me. I'll explain it back.
Yes, I understand.
Alright, nice. So somebody find the time it would take to charge the old battery for me. What's the time it would take to charge the old battery?
7,200 seconds. 7,200 seconds.
So
Let's find
I got 7,200.
good. And let's find the time it would take to charge a new battery. So that would be 9,000 over what, Karina?
Over 0.6.
Right, what is 9,000 over 0.6?
So I got 15,000.
Wait, ask Karina. Ask Karina.
Yeah.
Yeah, yeah, Karina. Plug that into your calculator and let me know what you get.
Karina, don't take my answer.
15,000
50.
15,000 people.
You get 15,000?
Yeah.
Alright, so if I want to find the difference in time,
You subtract the 7,200 from the 15 seconds.
yeah. By the way,
15,000.
you see this little delta over here just means different. So that means change in time. That's all. Right? Yeah. Yeah. Are you okay with that? And you should get your answer.
Yes, sir.
Yes, sir.
You'll get 15,000 minus 7,200. Plug that into your calculator and let me know what you're getting.
The same answer.
7,800 seconds.
But you
Yes,
see,
sir.
this is real work compared to this.
They are like the first
Yes,
one.
sir.
It's more, efficient.
It is more efficient, but the second one easier to follow along. Yeah. Right? Cool. So let me give all you some homework, right? Because I know all you love homework, and it's all you love homework.
No,
Practice
sir.
makes perfect, sir.
That is why
Yeah.
it's saying, Nikolai, after you get distinction on thing, you gotta come and I make a video with you. Like we sit down, and we talk like I interview you, and I give some advice to the next generation of students. Because you have a real good mindset. You see, and I'm not favoring anybody, right? But I just saying, if you want to succeed, you gotta do what you gotta do to succeed.
Yes, sir.
I feel like you and Shina understand what you had to do to succeed. Because Shina is a real workhorse as well. And I can't discredit Karina. I know Karina's been doing a bunch of things. But if all you want to succeed, you gotta you gotta do what you gotta do to succeed. Being average would not suffice. You have to do what you gotta do to rise to the challenge. Okay.
Yes, sir.
$66.
Wait, is that chemistry? Is that physics book?
Yeah, Terry David make his book.
Well, do we have that in the chat?
Not the Terry Alien.
I'm not sure, but I will send it to you if you want.
Yeah.
Alright. I take a screenshot of this. Wait till me just 1 second. So remember, if you want to check if it will become positively or negatively charged, what are you going to refer to? You're going to refer to the what?
The diagram that you showed us, the arrow going downwards.
You have
Can't
to,
remember.
you have to tell me the name, Nikolai. You have to tell me the name.
Electrostatic. Yeah, I don't know.
Electrostatic series.
Bruh. Okay.
This is very important. It's very important. I should probably put it somewhere like in bold. Know what I mean?
Yes, sir. Because I know I'm in this one here, sir.
Cool. Remember this. Let me It's a nice question, boy. So I suspect that some of you guys will not figure out these questions, which is okay. But please just try something. Hear what? An attempt is better than no attempt.
Yes, sir.
So this is all your homework. Okay, cool. So homework, or somebody take a screenshot and put it in the chat so they will know you have homework. Because I fed up here that excuse that no, we didn't have any homework. Okay, I'll take a screenshot.
Sir.
7. Okay, good. I tell you, if I didn't have exams on the 7th of May, I would have do a live after this, a physics live or something. Yeah, boy. But don't worry, Nikolai. After my exams, every day, I go and do a free 12, might be a 17-hour marathon, free 17-hour marathon / crash course for physics, maths, and hard maths. Yeah. So, mark that down in your calendar. Karina, mark that down too. Gonna be doing
Yes,
a
sir.
free 17-hour marathons for maths, physics, and hard maths. So, yeah, guys. Hope you have a blessed day. Take care.
Thank you, sir. Same to you, sir.
No problem.